Welcome everybody to another PLC riddle. And can you believe this is actually based on the AFI video that we did like 6 ago? I mean, it's really just kind of continued to snowball. I don't know if snowball is the right word. It's been some outstanding discussions on this. Now, if you're watching this live, don't hit the pause button. But if you're watching this later, here is the riddle that we're talking about today. So I asked which rung controls the output bit or wins. And yeah, so I have two rungs and these are two rungs that are in the same program. And it comes from a question or a discussion that I had going with someone. They replied back to my program scan video. This is why I map my I/O in a single routine in the PLC program. This way, if you have duplicate outputs, the last rung will overwrite anything that the first rung did. We call this the last rung wins rule. Now, I still can't decide whether he was trying to make me put this video out or he was legit. Now, I've talked to him. We've had this discussion. So I'm not ragging on him with this. But you guys know how I feel about rules. So I put this out, and actually I got a great response. So overall, we had over 250 comments on it. And there were a few that, well, first, I don't want to say anybody was wrong on this one, because this is really an exercise in understanding program scan. And this is one we actually do in a much more complicated way in our training center with the technicians. And you can tell once they go through this exercise, they come out a whole lot better troubleshooter. So whether you chose the first one, you chose the last one, or you realized, something doesn't seem right about this question, then you're okay. Because yeah, that's our whole goal, is to understand things when they're not working right. But I do want to highlight a few comments, Tom, and they were done several times, but I'm going to highlight certain ones. So this one came out quite a few times, but I did like this guy's comment. I'm not going to mention your name. You are showing your ignorance by having two outputs addressed twice. A good programmer would never do this. Well, I don't know. I consider myself a pretty good programmer. But there is one way that a good programmer can do this, and it's called making a mistake. And yeah, if you haven't made any mistakes, then chances are you're not trying hard enough. And yeah, here's my point. And everybody who just shouted, "Oh, you got a duplicate destructive bit, you can't do that," is if we accidentally do that and our code works the way we need it to, we're not going to go back and fix it. And I know some of you already have your hand on the keyboard and you're getting ready to type. Well, you get a warning for that. And here's the issue. We've already had this discussion. And guys, you got to stop putting the same thing each time. If you guys are just coming in watching one video, you need to go back and watch more of them. As we've already talked about, yes, down here we have a warning about a duplicate destructive bit. In fact, let me go ahead and hit the verify button. Oh, I can't hit the verify now. But you can see, yeah, we would have this warning. Now, the issue is in a large program, you're going to have many, many, many warnings, and you're going to have many duplicate destructive bit warnings. And we've already had a discussion about why that is so common. So we've got to be able to think through this when something goes wrong with it, instead of just being like, oh, somebody put a duplicate destructive bit in here, we're going to have to rewrite the whole program because that's wrong. So that was one. Now, the one that I do want to work on is, there was a group, and I'm hoping I'm eroding away at you, that said this will cause erratic and unpredictable operation. That's why it gives you the duplicate destructive bit warning. No, PLCs follow a very repeatable scan cycle and will always have a predictable result. It may not be the result you're looking for, but it will be predictable. And then finally, I already know some of you are getting ready to put, in the next probably 5 minutes, you're going to put a comment that, well, no, you were right. The last rung did win because it had the last effect on it. And I'm just going to put an analogy of Amber and me. If Amber is rung 0 and I am rung 1, and Amber has any effect on this, can I really say that I won? Let's say this was an argument. Could I say I won the argument if she had any effect on it? No, it would be a compromise. And the whole point of this exercise is to realize the PLC scan and its very repetitive process will determine the outcome, not the rung. So now let's talk through it. Oh, and yeah, because I know, yeah, if this is like the last two videos, I'm gonna get a bunch of negative comments. Can y'all like and subscribe to make me feel better? All right. So here is these two rungs. And so we have a switch bit and we have a start bit, a stop bit, an output bit. And the original comment was about IO mapping, that if you map your IO instead of using the actual inputs, it would cause a predictable outcome and rung one would control it. So I'm going to go ahead and map this to some PLC inputs. Now, typically, you would right-click here, add new routine, and you would probably have an IO mapping routine, but I'm going to do it right here. That way we can see everything as it's happening. So I'm going to bring a new rung down, and I am going to bring down, I go look for a 1, and then an output energize. And actually, yeah, I'm just going to copy that 4 times. And in this first one, we're going to use local :1 :I dot data dot 0. Whoops, that's an O. 0. And that is my, whoops, that is my green button. And that is going to be our start bit. And then I'm going to put local :1 :I dot data dot 2. And that is going to be my red button. And we're going to call that my stop bit. And then we're going to have our, oops, I skipped over the switch bit. So we'll do the switch bit next. And we'll use switch 1 for it. So that is going to be local :1 :I dot data dot 4. And that will be switch 1. All right, and finally, we have our motor output. So it'll be the opposite. We're going to put the output bit over here, and we're going to be going to local :1 :O dot data dot 0. Let's see. And that is our green button. I'm sorry, green light. Okay, so that gets it kind of like what he was talking about. And if you have been taught the last rung wins, and even now I know some of you are ripping out your textbooks, because I do know the last rung win is in a bunch of textbooks. And you know, this is one of those times, don't argue with your instructor. You're probably going to have to put that the last rung wins to get through your test, but this is going to show you it doesn't win. It's just the last thing that is able to affect it. So, whoops, let me just turn my switches off. There we go, because now we have real outputs. Okay, and so if you've been taught the last rung wins, you're thinking that rung 1 is going to control the output bit, and the switch bit will do nothing to the output bit. So I'm going to switch 1, and the green light comes on. And the next thing that most of you said was, well, it will switch it on, but now we have a seal in, and that's going to hold it until you press the stop bit. And when I switch 1, it goes off. So now you're going to feel like the ones of you that said the first rung wins was right. But if that was so, then if I hit my green button for my start bit, it shouldn't do anything. If I hit my green button, the green light's still going to come on. Now, a few of you said it depends on which one you do, because if you switch the switch, rung 0 would control it. If you press the green button, rung 1 would control it. If that's so, then when I let off this button, it should seal in, but it's not going to. And finally, just to add complete and total confusion to anybody that still thinks that one or the other rung wins, if I switch 1 to the right, if that is truly locking this in, Pressing the red button shouldn't do anything. I press the red button and it goes out. All right, now let's talk through it through program scan and understand how it actually works. So starting at the top, we're going to switch the switch off. This instruction right here goes and looks for a 1. We mouse over it, it has a 0, so it's going to be evaluated as false. And a false output energized does something. It goes and writes a 0. Where to? To the output bit. Then it goes to this rung, and it's going to start with this branch, and that's going to go look for a 1. Where at? At the start bit. It has a 0, so it is false. Now, when it gets to this corner right here, it's going to come down here, and it's going to do this one. This is going to go look for a 1. It has a 0, so it's also false. Then it's going to go over here and look for a 0 at the stop bit. It does have one, so it's true. Now, I don't have a continuous path of truths from left to right, and so that is going to go write a 0 to this. So both of these currently are writing zeros to the output bit, and then down here, we're looking at it to actually update the green light. Now, we're going to use our imagination for a second to talk through this next piece, because I'll switch the switch and let you see it afterwards. But let's say we switch this bit. Or I'm sorry, we switch 1, which is going to put a 1 in this. So this instruction goes, looks for a 1. It'll then have a 1, and it'll become true. And that's going to write a 1 to our output bit. Now, here's where we've got to understand that there's no magical hidden area that is being written to, and then later it's updating this. It is writing to this tag right here. So I right click and I monitor it. It is writing to this location right here. It's not writing to any little holding thing on this output energize. And mainly this thing right here is not reading from this. It is reading from this controller tag right here. And so it's going to come here. It's going to look for a 1 in the start bit. It has a 0, so it is false. It gets here. It goes to the lower branch. This is going to look for a 1 in the output bit, and it will have 1 then. And that is going to be true through here. So then this looks for a 1. This looks for a 0 at the stop bit, and that is going to write a 1 to the output bit. So at that point, both of these are. So I'm going to go ahead and switch 1. And now that output bit is on, and we can see it here. Now, about the seal in, because a lot of you said, well, once this is on, this will seal it in, and rung 0 won't matter. Well, let's use our imagination. So when we switch this, it's going to be a tongue-tied morning. If we switch the switch bit, or switch 1 off, this instruction is looking for a 1. At that point, it will have a 0. Here's why it's so important we understand that false instructions do things. A false output energize is going to write a 0 to the output bit. Now, that is the output bit over here in the controller tags. Then it's going to come down here. This is going to look for a 1 in the start bit. It's still going to have a 0, so it's going to be false. This is going to go look for a 1 in the output bit, and it's going to be over here, and that's going to have a 0 at that point. It's going to be false. So we won't have a continuous path of truths from left to right. So this is going to be false, and it's going to write a 0. And that's why when I switch 1 off, it goes back out. Now, let's talk about the start bit, because if we press the start bit, where a lot of you are thinking, well, no, this is the stronger rung. In fact, somebody did comment, this is the stronger rung. So it'll override this. But it doesn't override. This is going to do a very repetitive program scan. This goes and looks for a 1. Where at? The switch bit. It does not have one, so it's false. And a false output energized does go write a 0 to the output bit. Now, when I press that start bit, this is going to go look for a 1. It will have 1, so it will be true. And then it'll come down here. It'll look for a 1 here. This will be a 0. But I do have a continuous path of truths through this top section, and that's going to write a 1 to the output bit. And that's why when I press the green button, it also turns on the green light. Now, finally, we have the stop bit here, because it looks like if you switch one, and especially if you're thinking this is a stronger circuit, then it would definitely be on. But if you follow the program scan, then it's going to be really predictable. If we switch, man, it is a tongue-tying morning. Let me get some coffee here. I should have had a second cup of coffee before I started this. If we switch one, this goes and looks for a one at the switch bit, and it'll have one, so it'll be true. And that's going to write a one to the output bit. This instruction goes and looks for a one at the start bit. It'll be false. Then it's going to come here. It's going to go down here, and this is going to go look for a one at the output bit. It's going to have a one, so it's going to be true. I'm sorry, I pointed over there, but really I should be pointing here. It has one, so it'll be true. And that's going to write, oh, sorry, and then it's going to go here. And if I'm pressing the stop button, this will have a one in it. This is looking for a zero. It has a one. It'll be false. And a false output energize is going to write a zero. And that's why when I press the red button, it still turns the green light off. All right. Now, one other thing, because a lot of you did catch on. In fact, I didn't give kudos. Yeah, because, all right, I'm going to give kudos to Cameron McCoy. Now, 4 of you really did nail this down, but one, I think Cameron nailed it down the best. And also, he was either the first or the second one to really go through and get it. But the one thing that we do need to talk about is this output bit chattering when I press this stop button? And it absolutely is. And the way we're going to tell that is we're actually going to right click and we're going to copy our output bit rung that's turning on the green light, and I'm going to paste it up here. And then I'm going to make this the yellow light. And I'll finalize that. And when I press the green button, I'm sorry, when I press the red button, you're going to see that the green, oops, let me get that out of your way. The green light goes out, but the yellow light does not. In fact, let me just get this over on our face. And you can see here, both lights are on because of switch one, but when I press the red button, the green light goes out. So the whole point of this is I wish I could convince you guys that rules are not a good thing in BLC program. I mean, there are good practices and I get that, but when we make a rule such as, oh no, that's a duplicate destructive bit, you got to get it out of there. We don't take the time to understand it. And yeah, while this may have been put in there as a mistake, if our code works, unless you're in a classroom, if your code works and you are ready to get out the door, you're going to get out the door. You're not going to go back and review that code. So, I mean, I see duplicate destructive bits commonly in programs that technicians bring here. But also, I love this exercise because when we're in class, we do this exercise. It's a much more complicated version of this one, but they go into this and they're thinking just like you guys are of, oh, well, this one's the stronger one. Oh, last rung wins. You cannot get through that exercise, and they'll probably spend an hour on it without understanding program scan. And they don't realize it. They actually run into a worse case of it later in the video. I'm sorry, in the video. We're on video. Apparently I need a second cup of coffee for this. They run into a worse case of it in their training week, and they breeze right through it. And that's one of the gauges I use, where do you really understand it? So for everybody that's just like, duplicate destructive bits, stop, you can't do it. No, we need to understand them. That, in fact, for someone who said, it shows that I'm not a good programmer. No, that is what makes you a good programmer, when you can walk through the duplicate destructive bits. All right, now I apologize. I forgot to hit the public button on this live stream. So a lot of you are like got 3 minutes notice of this, but yeah, I normally do these on Monday and I have class this week, and we actually made a ton of different adjustments to our classroom. And I got thinking, I'm like, I'm going to walk in Monday and see something major that I have to fix, and I'm not going to have time to answer this riddle. We'll do one more riddle this year. It'll be next week. So be looking on Friday for a post about it. But okay, we do have a couple things in the chat. Hey, Mom, good to see you. See, Officer Husky, he was watching a video of yours from 5 years ago and noticed you. Hey, I was watching a video from 5 years ago and noticed you were alive. I've tried to set up a network switch with Putty and it requires me to enter a COM port number in the USB. I went into device manager and it doesn't mention a COM port number. Well, that means you need to install the drivers for that. I assume you have a USB to serial adapter, and yes, they will have a COM port number, but it's probably down under your unrecognized USB devices right now. And there are only like 2 USB drivers out there. And I think in the video that you were looking at, there is a link that will take you to one of the USB drivers that's probably used in like 90% of serial adapters. So anyway, that's all I have for today. Enjoy the rest of your Sunday and have a great week.